thanks to the organizers for inviting me to this wonderful and new for me meeting. But, well, I am a mathematician, so I'm afraid I will be perhaps too much formal for for many people in the audience, and moreover, well, some terminology might sound strange to physicists, but well, because I think it is there because just I learned like that in some papers scattered in the literature. Well, but my original motivation when I went into the subject well, some years ago was to try to develop for semigroups on non-commutative algebras and B of H, so the algebra of all bounded operators on a Hilbert space, all or a lot of the tools that are available for classical Markov semigroups on commutative algebras, well, for the study and the description of the dynamics. So this is, well, the mathematical definition of what I have in mind, and by the way, I call these Markov semigroups taking inspiration from the mathematical terminologies, but these are exactly quantum dynamical semigroups. And well, I think that well, everybody is familiar with this structure. Well, what is really an important point, because it looks like perhaps a technical property, but it well, it makes a big difference, is the time continuity. Whether one has the strongest possible continuity, so norm continuity, or only well, weak star continuity here. Well, here I wanted to say in the weak star topology, so but doesn't matter. And well, for these semigroups, there's, with respect to classical Markov semigroups, so what is known for classical commutative Markovian systems, well, the algebraic structure of the generators and of the operators arising in Lindblad representation of the generator, well, in my opinion, plays a very important role, because when one takes into account the algebraic relationships that appear in the generator, and I don't mean only the GKSL generator itself, then one can gain a lot of insight in the behavior of the system. And as in the commutative case, there are two important subalgebras of the whole algebra where the semigroup acts, which are the set of fixed points. This is well known also for semigroups on commutative algebras, that the set of fixed points play an important role in the ergodic properties of the semigroup and the asymptotic behavior And moreover, well, there is this object which, well, I called the decoherence-free subalgebra, but in the language of operator algebras, it is often called essentially the multiplicative core. So the subalgebra where the semigroup acts, the maps of the semigroup act as homomorphism. Well, this the set of fixed points usually is only a vector space, not an algebra, so one cannot multiply, but well, this one is. And what I already outlined is that one can obtain a lot of information on the behavior of the dynamics described by this semigroup. By the way, here I mostly insist on the action of the semigroup on operators, so in the Heisenberg picture. And but from the structure of these two objects, one can obtain information on invariant states, the structure of reversible states. So reversible states are, well, this again is a mathematical definition. It means those states that whose evolution is given by conjugation with EITH, E minus ITH. Where H is some Hamiltonian, perhaps not the Hamiltonian in the Lindbladian or the system Hamiltonian, but something else. And also in the asymptotic behavior, one can get information on the set of decoherence-free subsystems, which, well, I know in you know very well in this audience, and decoherence-free subspaces. So, roughly speaking, subspaces or subsystem where the evolution is essentially unitary. Well, first of all, some properties of this subalgebra, which is, by the way, always a subalgebra of the given algebra where the semigroup is defined, even if the original algebra is not B of H but an arbitrary von Neumann algebra. Well, this was the definition, but this algebra turns out to be invariant under the action of the semigroup. It has this multiplicativity property in the sense that if one multiplies an element of the algebra with, well, of the decoherence-free subalgebra and another one from the whole algebra, not of NT itself, then one still has the multiplicativity property. This is just by a standard trick of two positivity. And moreover, by the continuity properties of these maps, this algebra is also closed in a suitable topology, and so it is a von Neumann subalgebra of B of H. Well, it has a simple algebraic characterization in terms of the GKSL representation of the generator. Well, because if one has the usual GKSL representation here of the generator, well, this algebra is the commutant of this big set of operators. So these are Krauss operator in the completely positive part of the Lindbladian. And these delta n are the iterated commutators with the Hamiltonian in the Lindblad representation of the generator. Well, and even if the Lindblad, these operators here, the Krauss operators and the Hamiltonian in the Lindblad representation are not uniquely determined by the Lindbladian, these commutators and multiple commutators, with these commutators and multiple commutators, when one considers then the commutator of this set of operators, this is intrinsic and it is independent of a special GKSL representation of the generator. So this is also, I think, I don't know how much computationally is convenient, but one, at least when one works with pencil and paper, one can usually work out these commutators and find out what NT really is. And by the way, in general, it is not the set where the action is of the semigroup is like that, but is also contained. This is a technical problem related with the fact that these, where are they? Ah, here. This property is the homomorphism property, but one does not know from the beginning whether the homomorphism is also invertible or not. Okay. As about the set of fixed points, one has well, the standard properties, so it is a vector space, of course, but it may not be an algebra, which is the case also for semigroups on commutative algebras. It may or may not be contained in the decoherence-free subalgebra. It depends on the special example. In general, these two objects are unrelated. Nevertheless, projections of the set of fixed points belong to the decoherence-free subalgebra. There is the inclusion if and only if fixed points are themselves, form themselves as subalgebra. And in a special case, when there is a faithful normal invariant state, so a positive with unit trace density matrix, this set turns out to be a star algebra, and this is the simplest case indeed. And moreover, these some objects, like projection here, are easily identified looking for commutators of these operators in the GKSL representation of the generator. And so the well, since in operator algebras it is well known that when one wants to study the structure of an algebra, the first thing to look for are central projections. So those projections that come of a von Neumann algebra, I mean those projections that commute with any element of the algebra. Well, there were two reasons for which we started investigating the structure of semigroups in connection with this decoherence-free subalgebra. Well, one of them was well, a definition that is that has been studied in the mathematical literature or mathematical physical literature of decoherence. So saying, roughly speaking, that a system exhibits decoherence whenever it can be decomposed as a direct sum, so a strong topological property, by the way. It can be decomposed into two parts, and in one of these the evolution is unitary, and in the other part, well, the evolution goes to 0 as time goes to infinity, so it vanishes. And it turned out that in all the examples we found in the literature, it usually happened that there was a subalgebra which was of a special type on which the evolution was unitary, and well, something else, and but in the end this algebra always turned out to be of a very special type. So as I wrote here, an atomic von Neumann algebra. So this again is a mathematical definition. So first of all, it means that there are certain minimal projections in the center of the algebra. In this case, A would be n of t. And the algebra is the direct sum of type 1 factors. A type 1 factor means that each one of these is a full matrix algebra with a certain multiplicity. And this was always the structure appearing in the there. Well, and it turns out also, and this is essentially the starting point of this analysis, that the center of this decoherence-free subalgebra is contained in the set of fixed points. So in this way, well, since well, fixed points are trivial objects, you can pull them out or push in the action of the semigroup, like what you do with conditional expectations that go in and out the well, when you multiply for some random variable which is already measurable with respect to the sigma algebra with respect to which you are conditioning, you can pull this multiplication in and out the action of the conditional expectation. So it turns out that these fixed points are, sorry, that these central projection of the coherence-free subalgebra are fixed points for the evolution. And here, the fact that the semigroup is non-continuous plays an important role, because homomorphisms turn out to be endomorphisms, so they can be inverted. This property is also true, for instance, for analytical semigroups, if one wants to generalize the continuity, but I don't know whether for an arbitrary weak star continuous semigroup it is still true. And well, these von Neumann algebras are better than the other, because you can always construct what is called in mathematics a Umegaki conditional expectation, so a norm 1 projection, a normal norm 1 projection from the whole algebra to the smallest algebra. This is not the case, for instance, if you consider an algebra of multiplication by continuous functions. For instance, I don't know, L infinity, well, L infinity are not continuous, but an algebra of functions. And well, so there exists a conditional expectation always on to nt if it has this structure. And moreover, when there is a faithful invariant state, you have a conditional expectation both on fixed points and on the decoherence-free subalgebra. Sorry, I see that time is running fast, so I have to speed up a bit. And well, of course, this n of t has some relationship with the peripheral spectrum, because since in the end the action of the semigroup on n of t is automorphic, one expects that it is related with eigenvectors of eigenvalues on the boundary of the unit disk. Well, and this is the case, but this object has an advantage because it is always an algebra, while this one, so the linear space spanned by eigen vectors of modulus 1 eigenvalues is not. And well, and in general, even if there exists a faithful normal invariant state, these objects are may be different, and there are these inclusions in the infinite dimensional situation. Okay, so and well, if n of t has this simple structure, so it is an atomic algebra, one can, as I said before, obtain information on the semigroup, on the structure of the semigroup T or its invariant states. And this information in the finite dimensional case turns out to be essentially the same as in the structure theorem of Baumgarten and Naunhofer. But here, this perfectly works also in the case of an infinite dimensional Hilbert space. And so the first result that one can find is that, well, I am writing this for type 1 factors from the beginning, because the idea is always to work with type 1 factors, because they have this simple structure. And then, using the fact that well, one has these central projections in the algebra, the pi, in the previous slide, these pi's. These pi behave trivially with respect to the action of the semigroup, because they are fixed points. And one can take advantage of this and then divide the algebra into blocks, and each block turns out to be a type 1 factor. Well, and this is something that one can, I think, easily believe, because the action of the semigroup on n of t is automorphic. And so the operators in the Lindbladian act in a trivial way here in the multiplicity space of the factor. The action here on this B of k is well, is again automorphic, and so it is given by conjugation with E minus ITK, E ITK. And so one has this additional consequence on the structure of the Krauss operators. So they have to act in a non-trivial way only on the multiplicity factor of the representation of n of t. And well, the proof of this is quite simple, because n of t is already defined as, if you remember the first one of the first slides, it is defined like this commutator. Well, you are working inside a factor, so it is just a matter to remember that the commutator of objects like that are operators which are non-trivial in this component and in this factor, and trivial here. So I can, well, it is a short proof, so I can. So as a consequence, once one has this decomposition, so here, of the operators, when working on a type 1 factor, no, was the next, the semigroup, through the decomposition of the Lindbladian, well, this is just the unitary transformation of the space, so the final result is written here. Of course, on tensored operators, X explicitly by this formula. Of course, if the operator here is not a tensor product, well, this formula is no more good, because it involves some other term. But, so the generator then can be decomposed into something derivation and some Lindbladian, which we shall see in a while as some special properties. It is irreducible in the sense of semigroups. Irreducible means that essentially that if you start from any state, any density matrix, you evolve and you fill somehow the whole space with the supports of this. And the two objects commute. And so this has, well, at least we gave this interpretation that when the coherence-free subalgebra has this simple structure, there is, well, no other way of obtaining some something from an operator algebraic point of view complex, because you have always an evolution which is, roughly speaking, the tensor product of an automorphic evolution, and another one which is purely dissipative. We shall see now exactly in what sense. It is a part that essentially converges to a unique invariant state. And, well, but as a first result, the coherence-free subalgebra of this factor is trivial, is only identity multiples of the identity operators, because all the part where the semigroup acts in an automorphic way has been pushed here in the other factor of the tensor product decomposition. And of course, once one has identified this structure in n of t, one can also find what are fixed points in a more explicit way, because well, we will see this for this semigroup. The only fixed point will be the identity operator, and for this one, of course, it is clear what fixed points are. And by the way, something that I should say, and it is a small lemma in between, is that this Hamiltonian when there exists a faithful invariant state, this Hamiltonian or self-adjoint that appears here has also discrete spectrum. It cannot be an arbitrary self-adjoint. Well, and as a result, well, fixed points are what one can imagine, because you have eigenvectors, eigenvalue, pure point spectrum. The situation is quite simple. Well, if the decoherence-free subalgebra is not a factor but is atomic, then one can essentially extend the previous results by writing the decomposition with central projections. As I mentioned before, projection go in and out the action of the semigroup, and so it is easy to split the action of the semigroup and then recompose it. And well, as I mentioned before, this semigroup has a unique invariant state, or it is at least if there is a whole an invariant state for the whole semigroup, because it turns out to be irreducible in the sense of Markov semigroups. So in the sense that if you start from an initial state supported in some region, whatever the region is, after some time, and typically for any strictly positive time, you fill the whole space. And well, this means that you do not have regions where the evolution or the mass of the density matrix remains, so that you have no non-trivial, in the language of classical Markov processes, this property is called subharmonicity. You have no non-trivial subharmonic projection. Well, from this, from the structure of n of t, if it is of type 1, and well, for the moment we have the conjecture that whenever there exists a faithful normal invariant state, this n of t is always type, well, is always sum of type 1 factors, and so it is atomic. But under this assumption, one can also find the structure of all invariant states, and well, the result well, extends to the case of an infinite dimensional Hilbert space, the result of Baumgartner and Naunhofer in the finite dimensional case. Because well, and the key remark is that this Tm, which is on a single factor, where we're up here, it is this part which is purely dissipative, so there is no subalgebra on which the semigroup Tm acts as a semigroup of homomorphism. This semigroup turns out to be irreducible. Well, this is very simple because to prove, because one has, first of all, if there exists an invariant state, we have this inclusion. If one has a subharmonic projection for the semigroup restricted to the factor, then it is a subharmonic projection for the whole semigroup. But, well, this is a standard fact again. Subharmonic projections, when there is a faithful normal invariant states, are indeed fixed points. And so here fixed points have to be trivial, because well, we are acting on a on a given irreducible semigroup, and so as a result, this one has a unique invariant state. Well, sorry, I should say better, because here, in these factors, we have only trivial fixed points. And, well, consequence, again, to be a bit more clear, one has, if one considers, one reduces himself to factors, there is this representation, and so invariant states are what one can imagine. So density matrices sigma commuting with the Hamiltonian K, and tensored with the unique invariant state of this multiplicity factor in the representation, standard representation of n of t. Well, here again, the proof is very simple, because if one has an invariant state, well, let's stress again that I am working on a factor. So if rho is an invariant state, the partially traced states will be invariant, one for the automorphic evolution, and the other for the given, for the multiplicity, for the semigroup acting on the multiplicity factor. Well, so as a consequence, this rho k will commute with k. The set of fixed points here turns out to be trivial because the semigroup is irreducible, so it will be uniquely ergodic, so one has this convergence towards the unique invariant state. Moreover, from the spectral decomposition of the Hamiltonian for any element, for any trace class operator here, one can write down this decomposition and compute the limits. So in the end, any trace class operator will converge to something like that. And if the initial trace class operator is a state, one has the previous representation. Again, this also allows to find explicitly the basings of attraction of the invariant states. Because from this formula, one has the explicit limit of the Cesaro means of the of any density operator. Well, and if one has some of type 1 factors, well, it is just a matter again of decomposing the algebra, the atomic algebra, into its factors. On each factor you find the previous decomposition, and so all the invariant states turn out to be of this form. I will only mention, because time is over, I think. I have still 5 minutes. Okay, very good. Starting from this decomposition, one can also find explicitly the decoherence-free subsystems and subspaces that were studied by Lorenzo and collaborators, because, well, this indeed is her definition. Well, a decoherence-free subsystem is well, is identified essentially by a subspace which is embedded in the whole space through this formula. So there is this subspace, some factor, so it can be repeated several times by tensor product multiplication, and there is some remainder space. And moreover, what one wants is that the evolution is on the decoherence-free subsystem is automorphic. So just to compare the two situations, if one starts from n of t, one has this decomposition. These are the central projections of nt, which are also fixed points, and well, the minimal central projections indeed. And so the semigroup Delimbradian can be decomposed in this way. So one has a direct way for identifying what are all these KIs. So the system where, the subsystem where the evolution is unitary. And this is also, I think, I would say an almost constructive way, because you start from the Limbrad, the operators in the Limbradian. You compute the commutators, you have a certain algebra, you identify well, minimal projections, you identify the minimal central projections, and from this you end up with factors, and well, these Ki are the first space of each factor. This is constructive, at least from a mathematical point of view. I don't know whether it is computationally feasible, because if you have well, if the spaces have a very high dimension, I don't know whether this is a practical recipe or not. Well, and oops, what happened here? Well, as a result, indeed, one can see that a decoherence-free subspace is made up of the sum of a certain type of these subspaces, on each of which the Krauss operator in the GKSL decomposition of the Limbradian acts in the same way, and trivially, of course. So with here with the same lambda. It is important here to have the same lambda because, well, if you work out the computation with two sorry, where was it? Yes, with two of these blocks on which the Limbradian acts in a trivial way by scalar multiplication, but times two different scalars, then you have, well, this term which is positive, and so roughly speaking, it forces this matrix element to go to 0 when you act with the semigroup. Well, okay, but I think it is time to stop here. By the way, this is, well, I haven't written here the bibliography, but we have a group working in quantum probability at Politecnico of Milano. So if you go through the web page of our department, you can find the whole set of references, and also the work by my colleagues whom you know, Alberto Barchielli, for instance, and Matteo Gregoratti and Alessandro Toglio. Okay, thank you.
Okay, we have time for 1 or 2 questions. Madeleine.
Why you said that the spectrum of the Hamiltonian is discrete? Why is that?
Well, because you have a faithful, you have this property. What's going on? Sorry. No, well, but it is. Well, when you have this property, as a consequence, all spectral projections of ρ commute with EITK. And so each spectral projection of ρ, which is finite dimensional, is an eigenspace for K. So in this way, the spectrum has to be this.
Just another quick question. So is there also a nice theory like this for transient Markov chains?
Well, to tell the truth, not because for transient Markov chain everything vanishes to 0, and it is difficult to, in general, it is difficult to establish the same type of result. I mean, you have something like that for an arbitrary semigroup, but you should assume, as it often happens, that the transient part goes to 0. It is not always the case, of course. You need from the outset a good separation of the two parts.
And is it necessary that you have a spectral gap, or you could have no separation?
No. It is sufficient that the transient part goes to 0, also polynomially. It is not important how.
Yes.
Okay. Yeah.
Maybe, so it seems that you can also deal with infinite dimensional system.
Yes.
Yes, in this case. But
well, the inverse space is infinite dimensional.
Yes, in infinite dimensional system. But what about the operator in the Lindblad form? They have to be bounded or not?
Yes, they have to be bounded.
So every operator is bounded.
I am the starting point was that
okay.
Central projection, but I can finish in 30 seconds. Central projections of the von Neumann algebra are fixed points for the semigroup. This is true using norm continuity, because endomorphism turns out to be invertible. It is true also for analytic semigroups, but I don't know whether it is true for an arbitrary semigroup, because there you have this problem that homomorphisms are not necessarily invertible, and then the picture becomes a bit more complicated.
So it seems that with, for example, photon annihilator in the Lindblad operator, it's not so simple. Maybe it could be something like this, but you need that additional structure.
In this case, I think in the end the semigroup will be analytical. So I think you can do something like that, because you are essentially in the Gaussian case, so you can recover a lot of nice property. It is unbounded, but you have still a lot of algebraic tools. You have a good common domains for all the operators.
And if it is A square instead of A?
Well, with A square, perhaps still yes, with a lot of work. But
Okay.
with higher powers, I don't think so.
Okay. Thank you.
Okay. I'm conscious that there's a football game on today, so without further ado, I think we'll move on to the next speaker. But let's thank Franco again.